So the last thing to think about, this is more of just a thinker. I haven't decided if we're really putting this in the class yet. We're still, want to see how far I got today. It's really more of a big picture, interesting thing. Going back to the concept of the center of mass. Okay? So now you can do inelastic collisions, collisions where things stick. We'll do elastic in a couple weeks, and it's more complicated. And the demonstrations are more enlightening and dramatic, if you can imagine. Okay. Let's see. Exam uploaded on Canvas seemed to be a lot more about circular motion. Does that make, I don't know. I have to think about it. Yeah. Okay. Okay, so we've been doing these two masses in 1D, right? So we have mass here, and we have mass here. And they move, and maybe they hit each other, etc. Weird stuff happens, okay? But let's think about what is the center of mass of this thing. Like, say this is the origin, and that's plus x. And they're sitting at different positions. Before we talked about this point called the center of mass that was somehow important. Before it was what? It was where gravity acts. And it was also if you throw the thing in the air, the center of mass kind of acts like it's the point particle. It's where if this thing is a point particle, that's acting like where the point particle would be. And it'll just move as though it's a point particle. That's actually true even for two masses. Really? Really? Yes, I swear. Let's write the formula for the center of mass. 1 over the total mass times x1 times mass 1 times its position plus mass 2 times its position, right? That was where the center of mass would be, right? This is the origin. This one, if it's really big, it would drive the center of mass this way. If this one's really big, that formula will push the center of mass that way. If they're the same, it'll be in the middle, right? Okay. So what we could do with that formula is bring the big M over here. All right, equals M1 x1 plus M2 x2. So all it is center mass, brought it over here to the left. The big M is on the left now. Total mass times the center mass is equal to those two. But now let's take a derivative. All right. What is the derivative of M x cm? It's M times the velocity of the center mass. The total mass times the velocity of the center mass equals mass 1 times velocity 1 plus mass 2 times velocity 2. So these are the individual momentums here. But this is the momentum of the center of mass. Right? So what it's telling you is that you can think, well, just like in Newtonian forces, when we thought of the center mass as a special place where the force acts, it's also this special place where you could treat this as a point mass and it'll just go. So in all the collisions I did, if we thought about what's the center of mass doing, it's just moving. It's not doing anything. Okay? So like when this one was still and this one was moving, the center of mass was slowly making its way this way, but it was going slower than this mass, right? It was collapsing down to this position. So it's going slow, and then when they collided, it moved slower. The center of mass just went the whole time. It never budged, right? Because the center of mass of this system, there's no external forces. All the little bumping into each other, those are all internal forces. But the center of mass, it just glided the whole time. Okay, so we'll do more examples when we get to elastic collisions, but you can kind of think of it here. So, okay.